Go.
Hey everyone, we are Alien Supremacy. My name is Prem,
And I am Vedant.
and right now we are here to showcase our real-time live caption speech-to-text project. Um, let's first talk about the problem statement and why we chose this project. I'm sure you all have faced this issue with speech-to-text task. It's really frustrating when the model doesn't understand what you're trying to say. This is exactly what you're tackling right now. So our project's main mission is to make sure that the model doesn't just hear us, but also actually listens. And one of our research says that in 2024, the ASR market is expected to hit 8.53 billion US dollars. This actually highlights the growing demand for the accurate speech-to-text technology. And our vision is to explore the mechanics of voice recognition using advanced machine learning techniques to fine-tune the wave-to-wake model. We are actually fine-tuning the model using the LJ speech dataset, which actually contains 13,100 audio files. And here you can just, this is actually our first 4 rows of the dataset is just for the visualization purposes, but the dataset audio files are actually sampled at 22 kilohertz. Keep in mind that my partner Vedant will actually explain this in future when we talk about the fine-tuning process. Let's talk about the model architecture. So the model here takes a raw audio waveform as input, and this waveform is actually processed through a stack of CNN layers, and each layer extracts high-level features from the signal. Then the transformer architecture then processes this representation to capture the contextual information. The transformer uses self-attention mechanism to model the relation between all parts of the input sequence. Finally, a linear layer maps the transformer outputs to a set of probabilities over the target vocabulary. Also, the wave-to-wake model is actually a CTC model, and now you may wonder what the CTC model actually means. So basically, it stands for Connectionist Temporal Classification. It's basically an algorithm that's actually widely used in machine learning for training neural networks and also widely used for sequence-to-sequence problems where the input and output sequence have different lengths. It's particularly effective for tasks like speech recognition, where you need to map audio data. Now,
Now let me talk about how we fine-tuned this model and what was the process. The first thing that we did was setting up the environment, obviously, loading the data set, loading the pre-trained model. And after this process, if you remember, my friend Prem, my teammate Prem told us about the audio files being sampled at 22 kilohertz. Uh, the reason why we had to process the audio files was because the wave to vec 2 model only takes audio files of in of, with a sampling rate of 16,000 kilohertz 16 kilohertz. Hence why we process the audio files, normalize the audio labels for the ease of fine tuning and training the model on our custom data set. After this, we created a custom tokenizer and feature extractor so that we can easily pass our data set through to the training module, and it is faster and uses less computations to actually train our model. Um, After training, the evaluation matrix that we use, which is commonly used in speech to text task, was the word error rate. Word error rate basically means uh, what is the amount of percentage error of the amount of words that are in our transcription. There were some challenges that we faced, and we made use of the Hugging Faces trainer library to actually train the model and use the training of arguments. We trained the model, tested it upon uh, 200 epochs to 500 epochs to find the perfect balance where the model was not underfitting or overfitting.
okay, so our final approach involves real-time live caption speech recognition. You can watch this demo to see how it works. Can you understand me? I am talking to you. Okay, so from the demo you guys just watched, you can see how the model was able to predict my voice without any error. However, it still requires further fine-tuning process. In this slide, you can see the default model uh, output, which actually has spelling errors, but our fine-tuned model gives us the right output. In conclusion, our project shows how refining the model improves speech-to-text accuracy. Moreover, our future work involves exploring the documentation techniques and even maybe deploy the model in a real-world application to collect user feedback to iteratively improve the model. And we're done with the project. Thank you for
Thank you
watching.
so much. Thank you.